Hey physicists, we are starting off a new unit, which is the electric fields, electricity and magnetism. And our first chunk of that is electric fields. Put that at the top of your notes. I do want you to try this warm-up. It's based on topic 1 about error, and I think we might be a little rusty on that. So give it a shot. This is an old IB question from an exam. Maybe pause me and take a look at that. Okay, so we want to find the angular speed of a rotating object. We know the period with some uncertainty. So the angular speed is based on this formula from our formula booklet. That's not a big deal. They say, what's the percentage uncertainty? Well, if we calculate the angular speed, 2 pi is a number. So I'm going to write it as, well, yeah, it's 2 times 3.14. 1, blah, 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 blah. This is a constant, right? The only thing that's changing here is the period that we're going to put in, 0.50 plus or minus 5%. Since the numerator doesn't have any uncertainty, pi is always pi and 2 is always 2, there's no uncertainty here. We don't need to change anything. This is the only uncertainty on this side, so that is the only uncertainty you'll have in W, so I think 5% is the uncertainty. And yeah, sweet, okay. There's a practice packet that you should have. It's up on Schoology if you need it, but this is kind of the layout, and we're working out of Pearson's text. So when you walk out of here, I want you to understand and be able to do some problems with electric fields. And you know about electric fields. If you had a junky Christmas sweater and a balloon, and you rubbed them on each other and had them charged, and then you put the balloon near you, what happens? What have you seen before it when you're doing this? And if you charge up 2 balloons by like rubbing them on your annoying sweater, and then you hold them next to each other, what happens? Yeah. Well, maybe you've seen this before, where the balloon will attract to the sweater, and they'll stick together, right? So the balloon will actually, you can hook this to the sweater. And if you have 2 of these, and you've done this, like had 2 stuck to them, if you take these 2 away from each other, away from the sweater rather, put them near each other, they'll end up repelling, right? And they'll kind of push each other away. And that's because they're in the presence of an electric field. Much the same with your cat. And we'll talk about what's happening there and why that's happening. But maybe jot these notes down, like charge. All of this is happening because of charge. And charge is just this property of matter that feels a force. And we feel forces like the apple feels a force from gravity only because it has mass, right? If this was a particle without mass, like a photon, like a particle of light has no mass, doesn't feel a force because of a gravitational field. Yeah. But charged particles feel force from an electric field. I'll go over that in a second again. But bodies can have, or objects can have positive, negative, or neutral, no charge. When you have same charges near each other, they repel each other, and opposite charges attract. Fine. It's a scalar, which it just means it's a size. It doesn't have a direction. Yeah, it's just like how charged is it, not necessarily which way is the charge pointing. That doesn't make sense. So non-directional, it's scalar. And the unit of charge is a Coulomb. Yeah, it's one of our fundamental units. And so you've seen things like the Bohr model of the atom, where you have little electrons with negative charge zipping around the outside of a nucleus, which is partially made up of protons with positive charge and partially made up of neutrons with neutral charge or no charge. we'll get into why you have to have neutral charged objects in there. It helps the whole thing stick together. Otherwise, these positive charges would repel each other very energetically, very strongly. So you need multiple particles in there to help like stick together. We'll talk about that in deeper depth, but there is a reason that they stick together. The nuclear strong force is much stronger than the electrostatic repulsion that they feel here, and so they stick together. But we'll talk about that in more depth. So matter is made up of things with positive charge, neutral charge, and negative charge, protons, neutrons, and electrons. And they all have the same amount of charge. So every electron you've ever met has this charge. It just happens to be negative. And the protons have the exact same charge, which is really interesting, but it's positive. Yeah. And so they do attract each other. And that's one of the things that holds these highly energetic flying around electrons in towards the it's this electrostatic attraction where these try to attract each other. This is a fundamental charge. We call it little e, and the protons and the neutrons are heavier than the electrons. The electrons are a lepton, which means they're very light, and they're much more mobile. Yeah, so the electrons are the ones that move. Right? When you're talking about current, when you're talking about lightning discharge, all of those things, it's a movement of electrons. And I like this little demo. This is from PhET. You can search this if you like. Actually, it's already there. And so here's a balloon. Everything's mixed, nicely balanced, positives and negatives. Same with the balloon. But just because of the makeup of the material, with the wool, we can often peel off some of the electrons, right? With friction, you're actually like stripping them off frictionally and coating them to the balloon. And you saw the balloon now is negatively charged, is attracted to, you can't see, I'm pointing with my finger, is attracted to these positively charged region of the sweater, right? And the more charges we rip off of the sweater, the higher that attraction, right? If it's only a little bit of charge difference, peel only a few off, it's not attracted as strongly. Yeah. The other thing is even if you, like, it's easy to see that the balloon is attracted to the sweater whose charges it stole, negatively charged balloon, positively charged sweater. But also if you put it over towards like a wall, you can see the negative charges sort of deflecting the negative charges on the wall, and you'll end up getting a positively charged region because there's this electrostatic repulsion from the overall negative on the balloon, and it repels. You're welcome to open this up and play with it. I'll put the link on Schoology. All right. So an electric field is what we're most interested in, and a field is an area of space where there's a force experienced, but it's only experienced by particles with specific properties. So things with mass experience a force in a gravitational field. What makes a gravitational field? Other mass. That's a bigger idea. But an electric field exerts a force only on particles with charge, right? Did I write that? Yeah, charge. Yeah, so an electric field is this area in space where particles that are charged feel a force. Non-charged particles like neutrons don't feel a force there, right? Kitty in a force field. So therefore, if this is a charged sphere, like a metal ball with a lot of positive charges on it, if you have a little, they call it a test charge, a little positive test charge, this is making a region in space which this positively little charged particle will feel a force and be repelled, right? So that's this force is the electrostatic repulsion. The amount of that, how much it feels, is based on the field strength, E. Yeah, and we call that, it's the amount of force per charge, right? So how much, like, charges often come in units. So like if this is one single positively charged particle, how much force? if it feels a really big force, it must be in a high, a very strong field. If it just feels a little force, then it must be in a very small electric field, right? Surprise, surprise. So that's what all this means. The strength is the amount of force divided by the charge. You might get a lot of force, but it might be because you have a ton of these positive charges. So if you divide, you end up with, when you divide, you only get a little force per charge. And so it's really the ratio of the two. Yeah, so you should probably jot that in your notes. So, for example, calculate the force experienced by a charge of this magnitude in a field strength of this. Well, you'd say, okay, well, I know there's 20 newtons exerted. This is per Coulomb, per 1 Coulomb. I'm looking for the force it feels. And so let's see. Oh, sorry. And I have the charge. The charge is 2 times 10 to the negative 6th. We could multiply, and this is in coulombs. And if we multiply this to the other side, to both sides, you get 2 times 2, you get 40. And then times 10 to the negative 6, we've multiplied by 10, so this is really times 10 to the negative 5. 4 times 10 to the negative 5. It'd be 40 times 10 to the negative 6, or 4 times 10 to the negative 5. The c's would cancel out if this was multiplied into the numerator, and you'd just be left with newtons, which is great for force. So you'd get that many newtons. So what about a negative 1? This is half as much charge. So you'd say, okay, same thing, 20 newtons per 1 Coulomb. And we want to try to find the force. If you have negative 1 times 10 to the negative 6, you'd multiply and you'd get 2 times 10 to the negative 5. Newtons is your force, but it's negative means it feels the force in an opposite direction of that original. Neat. Okay, we show fields using field lines. So and the field lines show the travel of a positive particle. So here's a positive charged object, and we'd have field lines radiating out away from it, because if we put a positively charged particle near it, it would follow this line and get ejected away. If we put it there, it would follow this line and be thrown away, right? This shows you which way they radiate. Similarly, if you had a negatively charged particle, the two opposite charges would attract, and the field lines point in because they show you the attractive nature of the opposite charges. So this would attract in like that, right? And if this is sitting over here, it would follow this field line. If you had a positively charged plates and not just one object, if you put the positive charge there, it would repel off of these charges and be attracted to the negatives, and you'd see it flow. The positive charge would flow away. Yeah. So those are a way to show field lines. I think this is interesting too. Force gets stronger. It can be seen from the density of the lines. If you had two plates that were, if you had, let's do this. If you had this plate and this plate, and you wanted to show that the plate that I'm messing with right now is a stronger, it has more, is a stronger field, you'd put more lines in here. Higher density of lines means a stronger field, right? It shows a stronger field. So if you look here, out here, less dense field lines means there's fewer, you see fewer lines. Here in that same bubble there, I'm counting out here 1, 2, and a little bit field lines. Here I'm counting 1, 2, 3, 4, 5, 6, 7 field lines. Higher density of field lines shows you that the force gets stronger as you get closer, which makes sense. It's just a way to visualize it. All right, Coulomb's law just talks about how forces experience, or how charges experience a force based on each other. And this is the equation for Coulomb's law. You can jot that down. The Q is the amount, is the charge, like how much charges on each one of these little objects. R is the radius, it's the distance from the two charges. And K is this constant of proportionality, which is a physical constant. It's in the front of your booklets, and it's the same for everybody everywhere. Cool. So the thing that I mess up a lot is this square. I always forget to square the radius. We're not going to do the derivation. It's bigger than we need to, but this does make sense. As one of the charges increases, F increases. As the other charge increases, the force increases, right? If we make the charges really big and positive and negative, they'll really want to stick to each other. And also, if the radius increases, as we bring these charged particles, like if you had a positive and a negative, one of these and one of these, and you brought them far away, the farther away they are, the less they would feel the force of each other. So that's why the R is in the denominator. Okay? So, for example, here's a setup, two charges. Here's a positive charge and a negative charge, 2 meters apart. Find the force. Well, you could say, right, I know that the force is equal to the K term, 9 times 10 to the 9th, times Q1. It doesn't really matter which you call Q1, so this is 3 times 10 to the negative 9th, and times Q2, which is negative 5, times 10 to the negative 9th, all over R squared. R squared is 2, so 2 squared is 4, and then you could clean it up from there. Just be careful of how you multiply things. So this you could call over 1. You could multiply everything in the numerator, so it'd be 9 times 3 times negative 5. So negative 9 times 3 times 5. And then all over 4. You could put that all over 4. That's kind of interesting. And then times 10 to the, and then you could just add up the, ooh, that's interesting. So that's 0 and that's negative 9. So it would be, yeah, whatever that is, times 10 to the negative 9. It's a force, so its end result should be in newtons. All right, so you try that here. We have a 5 microcoulomb charge placed 20 centimeters from a different charge. Notice that this is pretty small and this is not in meters. Just be careful about that. Calculate the force on one, calculate the force on other, tell me the field strength. Okay, hopefully you paused me and worked through that. We can just use this for the force exerted on one of them. We plug in K, we plug in Q1 and Q2, which are these, and we plug in R. Now, micro is times 10 to the negative 6, so we can plug that in here. Right? So that's what we're doing here. That's the K value. This is the Q1 value. This is the Q2 value. This is R, and we remembered to square it. Yeah. And if you multiply, you get 11.25 newtons. Great, that's how much force. So one charge feels that much traction on the other. What's the force on the other one? Well, it's Newton's second law, third law, first law. Equal and opposite. Third law, sorry, all over the map. Equal and opposite forces, right? So like every force, there's an equal and opposite force. So they should both feel that force on them. And then find the field strength. Well, you can just say, I know this is the force per charge. Yeah. So what's the field strength this far from this specific charge? That's why we picked the oh, okay, all right. That's And then for the last one, what's the field strength 20 centimeters from the 10 microcoulomb charge? So this is the 10 microcoulomb charge. We know this is the 5 microcoulomb charge. I know that this distance is 20 centimeters. If we're looking for the field strength, we're looking for the field strength is the force per charge. And I know that the force is 11.25. 11.25. That 11.25 is pulling on the 5 microcoulomb force. Yeah. So I think this is over 5 microcoulombs times 10 to the negative 6. Okay. Yeah, there's your negative 6 and multiply through. It's because this force is being felt per 5 microcoulombs. It's being felt by this one, right? This is your test charge in the middle of nowhere, reading or feeling a force from the field given out by this charge. Okay? So it's a little fussy about which one's feeling which. All right. Some notes about electric fields and energy. If we were taking this charge and we were adding a positive charge one at a time to it, right? And the first one would go on there pretty easily. Let's turn it into these. The first charge would go on it pretty easily, but once you add these charges on and add more and more and more, it becomes harder and harder because the whole thing becomes very positively charged. And so eventually, it's harder and harder to push them on there. I have to lean the other way. Right, because this becomes more positively charged. It's more challenging to get those extra positive charges on there. So it becomes more and more difficult. So as we add more charges, we have to exert a larger and larger force over a distance. We're exerting a force over a distance, so we're exerting a force for a certain distance, I should say, which really means we're doing work. Yeah, that work is building potential energy in here. This has a lot of potential energy now because if one of these little guys escaped, these little charges escaped, it would turn into kinetic energy. We'd make it accelerate, right? So we're making potential energy, and specifically we're making electrical potential energy. So the amount of electrical potential energy we call the voltage, sometimes V, and a volt is a joule, how much work per charge, per coulomb. So a volt is the amount of energy per charge. Sometimes we call it potential energy as V times Q. It's the amount of energy in there is the pressure per charge, the amount of push per charge. Call it potential. Costume change. Apparently I get distracted easily. Another way to look at strengths of field is called potential difference, the PD, and it's the difference in potential in 2 points. It's really, you can think about it as the amount of work it takes to bring a charge from one place to the other. So if you think about taking this little positive charge and bringing him towards A from infinity, like way over here, trying to bring him to A, or try to bring him from way over here to B, it's a lot easier to bring him to B than A because A has much more positive charge. You can also think about that, and bringing it from the middle to B is a lot easier than the middle to A because there's more repulsion from this A. That idea of potential difference kind of tells you about the field strength. And another way to talk about field strength is with this. We looked at also that this was the charge per coulomb, and so this is another way to write it as like the potential the potential difference over the distance. So it's kind of like the pressure the charge feels over the distance between them. So sometimes we talk about electricity in terms of the electrons moving in the field, but sometimes instead of using joules for the energy, we talk about electron volts because it's more useful in this discipline. So an electron volt is this number. It's 1.6 times 10 to the negative 19, and it's when it's the energy that an electron gets when it's accelerated through a potential difference of 1 volt. It's a little bit arbitrary, but it gives us a starting point. We can use it like this. We have two parallel plates that are, if I move my head, 10 centimeters apart, and we want to find the field strength if there's 250 volts plugged into this. So the wall outlet in your house is 240 here in Switzerland, and so we want to see like how much, but we want to find the field strength. So we can use this idea that the field strength is V over D. Our 250 volts divided by 0.1, we have to turn that into centimeters to meters, and so you get volts per meter. So it tells you like how much pressure, essentially, how much push for every 1 meter that the charge feels. Yeah. And it says and the energy gained by blah blah blah, and so that we do this with it. So the energy gained we saw was also VQ. The potential energy was VQ, and so the change in potential energy is change in V over Q. So 250 per charge. The charge is an electron, right? We're in it's an electron. So we're using the charge on the electron and solving for that. Cool. All right, that's the ball game. We're doing 1 through 7 out of that packet. It's up on Schoology if you need it, and I'll see you later.